Finally, we start discussing a group of algorithms where the running time is in logarithmic scale. We are going to discuss the binary search algorithm, Euclid's algorithm, we will discuss exponentials, and rules for counting operations. We're going to focus on a specific class of algorithms, which are called the divide and conquer algorithms. These are algorithms that take the input space and split it into two, or actually it could be more than two, but in general the factor is two. So it will be splitting the search space into two, take one of them, and split it further into two, take one of them, further split into two, and work this way out. Of course, it's important from where you're splitting into two. It doesn't have to be exactly equal size pieces. And also later when you want to continue with one of these pieces, with which piece you're continuing, those are things you should be careful with. Such algorithms have complexity in the scale of log n. And the reason for that is based on the idea of trees. If you're splitting into two, these are called binary trees. These are topics we're going to be discussing in the following chapters. But we're talking about now a decision tree where the where the input is split into two pieces, and each one is split into two pieces, so we form a binary tree. And if you're talking about a binary tree that has n leaves, then the number of levels in a complete binary tree would be log n. And in each level, the divide and conquer algorithm will be performing an operation which is this splitting and then selecting one of those pieces. So the algorithm's complexity would be in terms of log n. So this shows a complete binary tree. As you can see at the very bottom, we have n leaves. And so let me show them with the pen. So the items here are the leaves. So this just looks like a tree. It's actually an upside down tree. This is like the root. If you just flip it upside down, you will see that it looks like a tree. This would be the root, and on the other side you will have the leaves. And these are called the branches in this tree. Altogether, this is called a tree. Since it has two nodes, at most two nodes, coming out of a single node, this is specifically called a binary tree, because we have two children from each node. And this is specifically called a complete binary tree because at the lowest level, which is depth 3, all possible positions are filled with a leaf. In this tree, we have 4 different depths. Depth 0 belongs to the root, and the others belong to either the intermediate nodes or the leaves. So we say the whole tree has a height of 3. You will note that we have 8 leaves. We're talking about a binary tree, so we are working on base 2. We have a height of 3. So we have 2 to the 3 maximum number of leaves, which is 8 leaves maximum. In this case, since it's a complete binary tree, we are using all of the leaves. That's why we have 8 leaves here. So let's start discussing the binary search. Binary search is one of the most basic search algorithms. It's a very simple algorithm. In binary search, we're trying to find a value in an array. We don't know if it's in the array or not. We're trying to find a value. But there is one very important assumption here. And that assumption is we're assuming that the array is sorted. Binary search works if and only if the array is sorted. So let's write it here. The very important assumption is the array is sorted. If it's not a sorted array, because of the algorithm you will see, binary search will not work. Okay? So with this assumption, one thing I can do is, the first solution would be straightforward. Start scanning from the first element and go till the end until you find what you're searching for. If you find what you're searching for, you can immediately exit. You're done. Or, in the worst case, what you're searching for is either the last element, or maybe it's not in the list at all. And also it's larger than the last element and it's not in the list. In that case, you would be doing n comparisons. Therefore, it has, in the worst case, O(n) complexity. Note that the average complexity would not be O(n). O(n) is the worst case complexity. What would be the average complexity in this case? Assuming that there is no bias, which means the probability of searching for any item in the list is equal. We are not biased on specifically searching for small values or large values or something close to the median. If that's the case, then the average behavior would be O(n)/2. But remember that O(n)/2, there we have a factor of 1/2. So if you're talking about O(n)/2, that means O(1/2) times n. But remember, I get rid of constant factors, so this is equivalent to O(n). So even in the average case, we still have an O(n) complexity. Okay? So that would be one approach, what we discussed in solution 1. Another approach is something that runs faster, actually. The idea here was actually introduced during the times of First World War, and it was based on a disease, again, something very related to what we're discussing nowadays. The idea was, if someone in the army has a disease, how do you find that person? You either apply the tests one by one, which is, as we discussed above, O(n) complexity, or I can do it faster. If I already have taken blood samples from every soldier in my army or in my team, I can get small samples out of those samples and put them all together and test them together. So this would be equivalent to testing the blood samples of all soldiers at once. But I will not do it to the whole army. I will split the army into two parts. Okay? So I will have two separate mixed samples. The first sample contains samples from n/2 of the soldiers, the first half of the soldiers. And the second sample is the mixed sample of the remaining half of the army. Again, n/2. So I'm looking at both of them. If, say, the first sample, the first mixed sample, comes out as clean, I don't need to do any more tests on that group, because I know all of the soldiers in that group were clean, otherwise that mixed solution would carry the disease. So in one test, I'm able to get rid of half of the soldiers in the army. So I have reduced the number of tests. Now I have the second half. I know the soldier who has the disease is in that group, but I don't know which one. So I take that sample, which is half of the army, and split it again into two. So that would be two 1/4 army sizes. Again, check each one. If one comes clean and the other one has the disease, again you're able to get rid of 1/4 of the army. So we now know that 2/4 of the army is clean with only two tests. And I have to search for the soldier who has the disease in the remaining 1/4 of the army. And this algorithm repeats this way until I keep on splitting. Note that in every split, the sizes of the portions are getting smaller and smaller. Finally, it will boil down to only two soldiers. So in one half, I will have one soldier, and in the other half, I will have another soldier. Now, either this or that has a disease. Of course, this example I explained works for the case of a single soldier in the army having the disease. There is the more generic case where there are more than one soldiers have the disease, but this is just the same thing applied in a different way. Now, anyways, let's go back, forgetting about the army and the disease, let's go back to searching an element in the array. Now, we're searching for a single value. So if I already have a sorted array, and if I find the middle element, the median in the list, in the array, what I'm searching for is either that a mid, the middle element, or something to the left or something to the right. Okay? So I apply only one comparison. Actually, you can take the case of equality either in the left part or the right part. Doesn't matter. The algorithm is same. But with one comparison, you're able to search either the left half or the right half, and you get rid of the other half. This way, you're reducing the size of your what we call the search space. The other algorithm we're going to discuss is a Euclid's algorithm. Let's say we're trying to find the greatest common divisor of two numbers, m and n. Let's assume for the sake of simplicity that m is greater than n. If not, you just flip m and n, just call them, say, k and l, such that the first one's always greater than the second one. Okay? So going with the assumption that m is greater than n, the greatest common divisor of m and n is equal to the greatest common divisor of n and m modulo n. This is what Euclid's algorithm says. Okay? And this works in a repetitive manner. Note that I have defined the greatest common divisor of m and n in terms of, again, the greatest common divisor algorithm. So note that I'm calling the greatest common divisor algorithm in a repetitive manner. So there is a recursion here. So let's see the example in the figure here. We're trying to find the greatest common divisor of 24 and 15. So I'm looking at greatest common divisor of 24 and 15. This is equal to the greatest common divisor of 15 and 24 modulo 15 is 9. So now I'm looking at the greatest common divisor of 15 and 9. Well, that is equal to the greatest common divisor of 9 and 6. So that's what I'm looking at, which is equal to the greatest common divisor of 6 and 3. So that's what I'm now looking at. And that is equal to the greatest common divisor of 3 and 0, and that's where I stop. So the recursive implementation of this algorithm would be as in here. Sorry, I should shift. So as long as m modulo n is not equal to 0, I call the same method in a recursive manner as n and m modulo n. But when it becomes 0, I just return n, which is the smaller value. In this case, it was 3. Okay? So this is the recursive implementation, but it's also possible to implement this in a non-recursive manner. So here we see the non-recursive implementation. Since it's non-recursive, I call the GCD function method only once, and inside the method I have a while loop, which is actually taking m modulo n and shifting these in a recursive manner. Please just run this algorithm by hand and you will see that it has the same effect. So actually recursion here is implemented using a loop here. It has the same effect. This is also an example of how you can convert a recursive method to a non-recursive method. Now this algorithm has complexity O log n. Why is that so? Now if you look at the second parameter, which is m modulo n, that is always less than or equal to m divided by 2. But, so m modulo n has to be not greater than half of m. Otherwise, you would be still able to have an n inside that remainder. That's why this is true. So after the first operation, n will be shifted as the first argument, and the second argument will be something that is less than n over 2. So this will keep on repeating. So in each iteration, you're reducing your search space at least by half. Therefore, you have a complexity of O log n. How about how we compute x to the power n? Well, one way of doing it is, of course, you have a for loop, you multiply the value x with the previous product, and you repeat this loop n times, actually n minus 1 times, and finally you will get the value x to the power n. But there are ways of solving this faster. Now, it depends on whether n is odd or even. Let's first look at the case of n is equal to even. That's easier. If you find x squared, you can implement x to the n as x squared times x to the n over 2. And note that this actually could be implemented also in a recursive manner. However, if n is not even, if it's odd, then it would be x squared times x to the n over 2, but you should take n over 2, the floor of n over 2, times x once again. So it could be implemented by the method given here. Note that it's again a recursive implementation. This is again log n complexity, because n is if n is odd, you need 2 multiplications, and the operations are repeated. But in each case, since you're dividing n by 2, the depth of going in this would be O log n. There could be another recursive implementation for x to the n, which would be, as I said, reducing. One could be by having a for loop, or in a recursive manner, you could just be implementing it by reducing the power by 1 in every stage. So it would have O n complexity. How do we count the operations? Now, if you have single statements but not function calls, well, the execution time of each statement on the CPU could be different, but whatever it is, it's always constant. So in other words, the time to do addition typically would be shorter than the time to do multiplication, but anyways, it's a constant value. It's not important how many microseconds, but it's a constant value. It's independent of the size of the number. So multiplying 2 by 5 and multiplying 2,500 by, say, 7,952 would take the same time. It's a constant value, so it's independent of the input. So for those, we will say it has complexity of 1, so it translates to 1, so when you do multiplication, it doesn't matter. For the case of sequential fragments, what we are looking at, as we did discuss earlier, we are looking at the maximum of those fragments and taking that one. If we have one loop iterating n times, where the loop body, I don't care how large the loop body is, but the important thing is the loop body has some constant complexity. Therefore, the loop body itself is O1, and the loop is iterating n times, then it has On complexity. However, if the loop body itself is dependent on the size of the input, say with some complexity of f of n, and the loop itself is iterating that loop body which has complexity f of n times, then we have a complexity of n times f of n. If we have two nested loops, say each one repeating with n times, it will be O n squared. If one is repeating n times and the other one is repeating k times, it would be n times k. And if we're talking about divide and conquer algorithms, for input size of n, such algorithms would have O log n complexity. However, if each step of that log n takes complexity of, say, On, then it would be On times O log n, so therefore it would be On times log n. How about, for example, checking if two numbers are relatively prime? Pay attention, relatively prime means the numbers need not be prime, but relatively against each other, they are relatively prime, which means they cannot be divided to each other. So the algorithm for finding that would be repeating in a nested loop of n times n, checking the greatest common divisor of the two and ensuring that their greatest common divisor is always 1. And you're counting this, and this rel value, pay attention, is initially 0. Tot is also 0. So in each iteration, you're increasing tot. So tot finally would be actually n squared. And if it's always 1, then this would be also n squared. So in that case, it would be 1. Otherwise, rel would be less than tot. So you would be returning 0 in that case. So the complexity of this algorithm is what? We have n squared here. But what was the complexity of greatest common divisor we discussed earlier? Remember, the greatest common divisor had complexity of log n. So I'm calling an algorithm that has log n complexity n squared times. Therefore, it's either n squared or if this is m times. So it would have n times m times log n.